Welcome back, Focus Learners. I am absolutely thrilled to have you here for another edition of our Explainer. Today, we're taking a high-altitude, tactical flight right over the Cambridge 606 additional mathematics syllabus. Think of this as advanced aerial combat tactics for tackling the absolute toughest exam questions they can throw at you. We aren't just going to passively stare at math problems today, no. We're going to break down the exact strategies, the advanced analytical tactics that literally separate a pretty good exam paper from an absolutely flawless one. We'll be analyzing Review Exercise 4, really dissecting how examiners construct these questions from the ground up, and most importantly, how you can systematically dismantle them.
All right, so here's our flight plan for today. We'll be tackling 4 distinct mathematical zones. First up, the combinatorics zone. Then we hit the algebra zone. After that, it's the geometry zone. And finally, we'll land in the application zone.
Okay, let's dive right into this. Zone 1, the combinatorics zone. This is where we look at exactly how we arrange and select finite sets of items.
So take a look at this word from Review Exercise 4. Question 1, algorithm. It's a 9-letter word, right? And it's got 9 completely distinct letters, no repeats. Now, the examiner asks us to make 4-letter arrangements out of this. On the surface, you're probably thinking, okay, simple permutation problem, no big deal. But honestly, it sets the stage perfectly for understanding exam boundaries. It's the baseline.
Notice the sheer power of constraints here. The exam is almost always going to contrast a no-restriction scenario with a highly restricted one. No restriction simply means picking any 4 letters from the 9, just a straight-up permutation. Easy. But look at that second condition. Starts with G and ends with T. Whoa, suddenly you have to lock down the boundaries. The first and last spots, they're taken. You are no longer choosing from 9 letters, you're actually choosing from the remaining 7 letters to fill just those 2 middle spots. Highlighting these constraints and reading the fine print, that is exactly how you lock down the boundaries of the question and secure those marks. Oh, and before we continue, subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Trust me, you'll want those tactics in your feed.
All right, let's level up to a slightly more complex scenario and see how this logic builds. Question 4 asks us to assemble a 7-person panel from a group of 10 police officers and 15 civilians. That's step 1, pure selection. And selection means combinations, right? Because we don't care about the order yet. But then, boom, step 2 drops in. From that newly chosen 7-person panel, you must select a chairperson and a secretary. So, the absolute crucial point here is understanding scenario building logic. You shift from combinations, where you're just choosing a group without caring about order, straight into permutations, where the specific roles of chair and secretary mean order absolutely matters. These independent choices build upon one another sequentially, like stacking blocks.
And you know, this brilliantly illustrates our next combinatorics trap, the dreaded at least constraint. In question 3, we need an expedition of 8 scientists, chosen from 12 ecologists and 6 meteorologists. Now, if the team must contain all of the meteorologists, that's super easy. You just take all 6 of them, and then pick 2 ecologists to make 8. Done. But what happens when the exam says the team must contain at least 3 ecologists? Listen carefully. That phrase, at least, is a massive trigger warning. It escalates a single, simple calculation into multiple, additive scenarios. You literally have to systematically account for exactly 3 ecologists, then exactly 4, exactly 5, and so on, and then add all those combinations together. Honestly, it's an organized accounting task just as much as it is a math problem.
Moving on to Zone 2, the algebra zone. We are officially stepping into the abstract world of predictable sequences and progressions. Here, the exam really tests your ability to juggle formulas. On the left side, we've got an arithmetic progression. We're told the 10th term is -27, and the sum of the first 5 terms is 40. With arithmetic, you're dealing with common differences. It's linear. But on the right, we have a geometric progression, where the sum of the first 2 is 10, and the third term is 9. Over here, you're hunting for a common ratio. It's exponential. The ultimate strategy for both? Translation. You need to immediately convert that English text into 2 simultaneous algebraic equations based directly on your sequence formulas.
So, once you've done the hard work and solved for your first term and common difference in that arithmetic progression, the examiner throws a specific target at you, -212. They tell you this is the nth term, and your job is to find the value of n. This completely tests your reverse engineering skills. You set your nth term formula equal to -212, plug in your knowns, and carefully solve for n. And here's a pro tip. If n doesn't come out as a clean, whole number, you know immediately, right then and there, that you've made a calculation error earlier on. It's a built-in safety check.
Then, question 7b hits you with this. Find the sum of the 100th to the 200th terms. Now, a novice might totally panic here, but a focused learner, they know the chunking strategy. You are absolutely not going to calculate 100 individual terms. Nobody has time for that in an exam. Instead, you use your sum formulas to find chunks of progressions. You calculate the grand sum of the first 200 terms and simply subtract this sum of the first 99 terms. It is a beautifully efficient subtraction of overlapping areas. Just genius.
But hey, algebra isn't just sequences. It's also about expansions. In question 5, you're asked to find the first 4 terms of a binomial expansion in ascending powers of x, and then use that to find a specific coefficient, the coefficient of x cubed in a multiplied expression. The step-by-step extraction required here is absolutely vital. You do not waste precious exam time expanding the entire massive expression. No way. You only multiply the specific terms from the first bracket with the specific terms from the second bracket that will result in exactly an x cubed term. It's surgical precision over brute force. Okay, stop scrolling for just a second. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, back to the flight path. Zone 3, the geometry zone. This brilliantly illustrates how we move into translating numbers into two-dimensional space using vectors.
Let's start with a foundational definition that you absolutely must have locked in your mind: a position vector. It's a vector representing the position of a point relative to a fixed origin, usually labeled O. So, in question 8, point A has a position vector of 2i minus 5j, and B is 6i plus 9j. This means we are anchored. Every single movement, every line segment we calculate is ultimately tethered to that invisible origin point of 0, 0. It's your mathematical compass.
Now let's move to question 9. It's this brilliant quadrilateral puzzle from a past exam paper. We have vectors A, B, and C acting as our outer framework. But the real challenge? That lies in the internal constraints. Point M sits inside the shape, cutting lines into specific ratios. AM to MC is 2 to 1, and OM to MB is 3 to 2. You have to treat this geometry like a systematic puzzle just waiting to be dismantled. Ratios basically mean fractions of a total path. You are literally drawing paths with your pencil, linking origin points to destinations using these exact fractional steps.
So the crucial point the exam is testing here is your flexibility in routing. It asks you to find vector OM in terms of A and C, and then immediately after find that exact same vector OM in terms of B. Think about that. It's the exact same geometric path, the exact same destination, but expressed through completely different vector combinations. It's like taking 2 different highways to get to the very same city. And here is the golden rule. Equating these 2 different expressions for the same line is very often the secret key to unlocking the final marks in complex vector geometry.
And now we arrive at the climax. Zone 4, the application zone. Let's put all these abstract concepts into motion with kinematics.
This is the ultimate challenge from question 10. It's a highly dynamic, real-world kinematics problem. A ship leaves a port. Hours later, a helicopter launches to intercept it. We aren't just dealing with static positions anymore. We have the complex, real-time interplay of time, speed, distance, and bearing. Like I said earlier, it's mathematical aerial combat.
The absolute first tactical move here is locking down the timeline. The ship leaves port P at 1300 hours. The helicopter doesn't leave its base until 1700 hours. That is a massive 4-hour head start for the ship. We are defining our variable T as the hours after 1700. Mapping out these critical chronological events is essential, guys, because it dictates the time variables in your position equations. The ship's travel time is going to be T plus 4, while the helicopter's travel time is just T. Now, take a really close look at the ship's specific velocity vector, 7i minus 24j kilometers per hour. This isn't just a random coordinate, it's a wealth of hidden data. From this one single vector, you use Pythagoras to extract the absolute speed of the ship. Then you use trigonometry, specifically the inverse tangent of 24/7, to find the exact compass bearing it's traveling on. The examiner fully expects you to pull real-world physical properties right out of these abstract unit vectors.
To secure those final 5 marks of this rigorous intercept calculation, you must follow a strict step-by-step unpacking.
First, calculate the initial speeds and bearings. Second, form a generic position vector for both the ship and the helicopter at any given time t. You basically take their starting position and add their velocity multiplied by time. Finally, the magic step. To find an interception where they literally crash into each other, the two position vectors must be exactly equal. You equate the I components, equate the j components, and solve the resulting algebra for time t.
And to actually execute that, you need the helicopter's precise initial constraints. Its starting base position is way off at 409I plus 141J relative to port P. Its velocity is negative 120I minus 103J. By combining the starting position with its velocity multiplied by our time variable t, we create the helicopter's flight path equation. We then set that equal to the ship's path equation we built just a moment ago. Solving that resulting algebra gives us the exact hour and coordinate of the intercept. It is just a brilliant, incredibly satisfying synthesis of algebra and vector geometry when it all clicks.
Which brings us to our core takeaway for this entire explainer. Success in Cambridge additional mathematics doesn't come from just mindlessly memorizing formulas. Mastery comes from recognizing exactly which zone of math logic you are standing in and systematically applying those distinct rules to complex, ever-evolving scenarios. It's about spotting constraints, routing geometric paths, and keeping a cool, tactical head when time variables are introduced.
So, I leave you with this final, provocative thought. Look back at the 4 mathematical zones we conquered today: combinatorics, algebra, geometry, and application. Which of those 4 mathematical zones challenges your personal logic the most? And more importantly, having seen the structure behind the questions today, how will you adapt your exam strategy to conquer it? Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly explainers. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every single comment. Like and share this explainer with a study partner. Ace the Exams, your Cambridge success starts here. Grab some past papers, put these tactics to the test, and keep learning.